All right. Good morning, everyone. Today is January 6th, 2018, and this is the John Chappell Natural Philosophy Society Science Chat. I'm your host, Franklin Hu. So today we have pretty much an open forum. Bob did send me a topic he would like to discuss. So, Bob, why don't you go ahead?
I have a couple of presentations. They're short. Can we share screens?
Well, let's see whether I can't promote you. See if I can do that. Let's see here. See, I'm clicking on your. This is where not having the PC interface is kind of difficult. See here, manage participants. So Bob Gray, I'm going to promote you. Okay, so now you are a presenter. So you should be able to share your screen now. There we go. We see that.
Oh, when do I? Okay. I continue to hear comments about the unipolar generator, which has me scratching my head why people would make such comments. So I figured I'd throw together a couple of slides on at least my take on the unipolar generator. So here's an experimental setup that we all know. I stole that from Wikipedia. So you have a rotating conducting disk and a magnetic flux field perpendicular to the disk and a circuit which is in the same plane as the magnetic flux lines, if you will. I don't like that terminology, but that's it. But anyway, there's since there is no B flux through this circuit, people scratch their head and wonder how can there be any induced EMF. So first, here's a very brief, I won't do a lot of math this time, just very brief. Here's a derivation of EMF from Griffith's book. He starts with this curl of E is equal to minus partial of B with respect T with respect partial of B with respect to time. Then he does integration over the area enclosed or defined by the circuit. It's a closed circuit. Then there's the application of Stokes' theorem on the left-hand side, which changes this integration over the area to an integration around the boundary of the circuit. And that on the left is then defined as the EMF, and on the right is a time change, time derivative of a magnetic flux through that area. But what you got to realize is that not all circuits are closed circuits. This is not the most general way to define EMF, and therefore it's applicable, that derivation in the results is only applicable for a special case where you have a closed circuit and where there's non-zero magnetic flux through the area defined by the closed circuit. You don't always have that. The unipolar generator is one case where you don't have that. And of course, my take is, hey, you know, in Weber electrodynamics, which I prefer, there's not even anything like a magnetic induction field. But anyway, a more general definition of EMF would be this equation. EMF is defined to be 1 over the charge, the integral, line integral of the force on the charge from point A to point B. That does not require a closed circuit. Okay, and F here is the force between possibly moving charged bodies. So EMF physically has nothing to do with enclosed magnetic flux. So here on the conductive disk, we can kind of think of that as a lot of conducting spokes all jammed together to define the conducting disk. And for the magnet, we use the concepts from Stokes' theorem. A magnet can be approximated by a quote-unquote equivalent current loop. And I get that here, show that on the left. Here's a magnet. A magnet is composed of a lot of small current loops all jammed together. And if you try to integrate all over these individual current loops by something similar to Stokes' theorem, really that's quote-unquote equivalent to just one big current loop around the perimeter. So essentially now you have this setup where you have a conducting spoke which is rotating within a, in this case I draw it within, but you have a current in a conductor generating, if you will, the quote-unquote magnetic field. But now you can see that we're really talking about the interaction of the charges in this conducting spoke and the charges in this current loop. So here you'd use the total EMF around a circuit. A closed circuit is just the sum of each individual segments of that circuit. In this case, I've divided it into 4 segments. And the EMF in segments 2, 3, 4 are 0, whereas in segment 1, it's just that line integral from A to B of the force along that line per unit charge. Okay. In case 2, where you have the magnet rotating with the disk, what happens is that you just add an additional component to the current in that magnet wire, or the magnet as a wire. And the components are the rotational speed of the disk, but there's electrons in that conducting disk and protons. And so they cancel out and you're left with the same current magnitude, regardless if the magnet is rotating or the magnet wire is rotating or not. And that's why rotating the magnet with the disk produces the same result as the disk rotating and the magnet not rotating. Okay, so some comments. Flux cutting is a very bad concept, but it is often very useful. EMF as a change in B flux is not really the general concept. The general concept is charge particle interaction. So be careful using Stokes' theorem. It requires closed circuits. Let me see. All electrodynamic forces come from charge body to charge body interactions and not from mathematical concepts like magnetic induction fields or flux linking. And when I say charge body, yes, I do include its electric field. So to me, a charge body is not just like a billiard ball or a solid or a point and the field is separate. No, I take the whole thing, including its field. When I say charge body to charge body interactions, it includes the interactions with this electric field. And I keep saying over and over, you're probably sick of me saying it, no physical magnetic induction field. But actually, in reality, this whole thing, why we don't have, for me anyway, a quantitative analysis is because the whole setup is much more complicated. The actual path of the currents in the disk is not necessarily along the radial spokes. There are no spokes. That's just an approximation. And the force on the charges in the disk due to the motion of charges in other parts of the circuit, for example, that paths 2, 3, and 4, which I showed in the previous diagram, those have not been taken into consideration. But once those charges start moving, then they're interacting and with all the other moving charges. So the whole thing is more complicated. This has just been a simplification. An analysis of the unipolar generator using Weber electrodynamics has been done. It's in the literature by Professor Assis in a paper called Unipolar Induction in Weber's Electrodynamics. That's the reference there back in 1994. So those are my comments on the unipolar generator. The other thing I wanted to mention today, get people's comments on, is, what's this? Yeah, here's a experiment that I came up with, conceptual experiment on induced EMF, and wonder if there'd be any interest in this experiment. The goal is to demonstrate that induced EMF can occur without a magnetic induction B field in the lab frame. No magnetic field whatsoever, and you can still get an induced EMF. Second goal, demonstrate the ability of Weber's electrodynamics to predict qualitatively the results of the proposed experiment. So this experiment would be to consider two concentric rings. I'll have a picture of it in the next slide. An outer ring, which is not conductor, has a larger radius than an inner ring, which is a conductor. And you put an LED or a light bulb in series with that conducting inner ring. The non-conducting ring is uniformly charged to a high voltage, so it is not charge neutral. Then there's two cases, the charge neutral conductive ring with the LED is spun up or braked or spun down, while the charged non-conducting ring is held fixed, or the other case where the charged non-conductive ring is spun up while the conductor and the LED is held fixed. So in both cases, there are no magnetic fields. I'm sorry, not in both cases. In case A, there is no magnetic field, okay, in the lab frame. There is none. And yet, the question is, will that LED light up or not? And if so, under what conditions? Here's the setup. So the outer ring connected to a high voltage source. I don't know how to do this experiment exactly. How would you put a net charge on this outer non-conductive ring uniformly? I don't know. The inner ring would be conductive, maybe a thick piece of wire, solder in an LED or a light bulb in series. There's no magnetic components here at all. And so in case A, spin up this inner ring. See if that light bulb or LED lights up. Case 2, hold this inner ring fixed with the LED fixed, but rotate the outer charged non-conductor. Okay, what do you think the results are going to be? I think the results, if you're looking from Maxwell's point of view, case A, the rotating the charge neutral ring, that there is no magnetic flux through the ring, there's no change of flux, therefore the LED would not light up. I'm thinking of it from the Maxwell point of view. However, in case B, where the non-conducting but charged up ring is rotating, that would generate a magnetic induction field, and as its rotational speed changes, increases or decreases, there would be a change in the magnetic flux over the area defined by the conducting ring, and therefore the LED would light up. That's the way I think the Maxwell point of view would go. From a Weber point of view, rotating the charge neutral ring there is a relative acceleration between the conductive electrons in the conductive ring and the charged ring. So the LED would light up in case A. That's different from the Maxwell point of view. And in case B, where you rotate the charged non-conductor, it's the same as case A, because you simply have relative accelerations. And so the LED would light up again. So in Weber, I think the LED would light up in either case, but in Maxwell, it would only light up in case B, where the charged non-conductor is rotating. You see, so Maxwell, for case A, the rotating conductor, you have to change the frame of reference into the rotating frame of reference of that rotating conductor in order to see a magnetic field. That rotating frame would then not be an inertial frame. My criticism is, why isn't Maxwell electrodynamics symmetrical? Why should it matter which ring is rotating in the lab frame and which ring is stationary? For example, if you and I are out on the sidewalk and I walk away from you, how is that really different from you walking away from me in the opposite direction? Or take two electrons. If one is linearly translated away from one electron versus the second electron being linearly translated away from the first electron, what's the difference? In the physics, I don't see the difference. That's my criticism of Maxwell's approach. In Weber, there would not be a difference because it is simply that relative difference and that the change of the relative distance or relative acceleration which matters. So anyway, wondering if there's any interest in somebody actually trying to do this experiment, or if somebody knows in the literature that this has already been done and what the results are. And then I just have an equation, what the equation would be in Weber electrodynamics for the induced EMF. And you can see here it's the difference in the velocities of the two rings, or the difference in the acceleration of the two rings. So that's what I had today, and was wondering if anybody had any comments on either of these.
All right, well, that's an interesting experiment. Now, the source of a strong electrostatic field that I normally use is a Van de Graaff generator. So that can generate about 300,000 potential volts difference for your experiments. So the trick would be figuring out how to put that on a ring and keeping it there. Now, I don't think it necessarily matters that the ring is conductive or not. If you were to create a ring and you touch your Van de Graaff generator to it, it will take the charge and keep it.
Right, but the problem is that there's back forces. You know, so you want to make sure that the charges on that outer ring don't move. So if there's a, you know, Newton's action-reaction kind of complementary there, which is why I say it should be a non-conducting ring, which is charged. So you can control the motion of those charges to some extent.
Okay, well, I think you could probably charge a ring of styrofoam just as easily as you could charge a loop of wire. One of these things, when you play around with the electrostatic generators, you find that nothing is an insulator, basically.
Yes, that's true too.
Plastic holds charge quite well. So once you charge up your piece of plastic, you can go play with it, and you can see it holds its charge for quite some time. But so that's an idea. You can use a Van de Graaff generator to at least get your initial charge. Or what I've done is that you can just take simply a ring of plastic and rub it against, something that's in the like a silk or whatever, and just charge it up, and then you can use that. Although I think that the amount of voltages that you would be talking about here would be way less than can light an LED light bulb. So probably you're going to have to find a way to just put a sensitive voltmeter in the circuit.
Yeah, I think it would light up only briefly anyway, because I'm expecting it to light up only during the acceleration, not constant rotation.
Well, if you've ever tried to light up LED with low amounts of energy, you would find that LED takes quite a bit of electricity to light up. So I would doubt that any such setup like this, I mean, even if it works to generate electricity, it would be very difficult. You wouldn't be able to light up the LED. It takes a lot of energy to do that. But right. You can measure very, very, very small voltages with just simple digital voltmeters.
Okay.
I would suggest, I'm kind of wondering that you can do simple things like spin an LED or a wire loop in the presence of a Van de Graaff generator. That's something that can be easily done. Although I'm not have to still try and measure any induced current. Although I'm thinking that the problem with being a loop, that it would probably, even if there is an induction effect, it would probably reach equilibrium. It might reach equilibrium because it's a loop pretty quickly. So it would, you might have difficulty picking that up.
I would suggest spinning the loop very quickly to high speed and then braking it. Put a brake on it and just stop it real suddenly. That acceleration would be very large, and you ought to be able to see a spike. If you had some kind of, as you're suggesting, some kind of voltmeter or some other device to be able to register those kind of spikes. I thought, a diode, I thought was took much less energy than a incandescent lamp of any kind, and then a photo detector just to see if it gave off any kind of light. But
yeah, I was kind of thinking about that in terms of a project where I would build like an AM radio receiver, because I got one of these like 101 kits, and instead of powering a little piezoelectric earpiece, actually hook it up to an LED and power the LED with the ambient radio waves. But you find out that there's just not enough power to, even though an LED takes a much less energy than an incandescent lamp, there's just not enough juice to get it to do a real thing.
Yeah.
I mean, actually, I was thinking about that this week, and it turns out that there's a company called, I think, FreeVolt or something, that's actually done this. That they actually built a device that harnesses the local Wi-Fi and radio transmitters to generate enough power to drive a carbon monoxide detector. And so we have this device about the size of a cell phone, but doesn't require any batteries. Apparently will run for as long as there's ambient radio waves to be harvested.
Yeah.
So that's not exactly on topic, but I thought that was an interesting thing that I saw this week. And they actually sell this thing on Amazon for $30. So if you want a device that just basically harnesses the ambient energy around you to do a very practical thing, which is to be a constant pollution monitor that hooks up to your phone and the phone, and that's a lot of electronics to support, because you got to support Bluetooth transmitter in order to do that. So they're generating a non-trivial amount of power there. But that'll be my initial comment. So what do other people have to say about Bob's experiment or about his unipolar induction conclusions? Anyone else out there?
I don't know enough about it to be able to comment intelligently, so I'm just keeping quiet.
Okay. Well, I think Harry's here, and this is totally down his ballpark, I think.
I have a question for the group. I'm looking for a reference that would describe how you go from classical electrodynamics to quantum mechanics in the non-special relativity case. I know you you put in the vector potential into the Hamiltonian, and I've done all that years and years ago as a student, but it was always with the special relativity. Like chapter 1, here's review of special relativity. Okay, now here's quantum field theory with, classical electrodynamics. I can't find a good quote unquote good reference that does it in the non-special relativity case. Anybody got a reference for me?
That almost sounds like a question for Bill Lucas, who's here, I believe.
Well, first of all, there's some things that need to be discussed. In the Weber's version of electrodynamics, everything is in terms of the radial separation, the velocity, and the acceleration. In Maxwell's, it's all just radial and velocity. And but Maxwell, what we call Maxwell is really done by Oliver Heaviside, because Oliver Heaviside did it in terms of vectors instead of quaternions. But if you do it properly, according to what people like Isaac Newton said, you should use the complete set of the empirical laws of electrodynamics, and there's 6 of them. And Oliver Heaviside only used 4, and then he threw away the terms that he needed because he had more unknowns than he had equations, so he had to throw away some terms. But what I did in my book, The Universal Force, Volume 1, is I used the complete set. And if you do that, you can't use the vector potential, and you have to use the energy potential. And when you use the energy potential, you get the radial term, the velocity term, the acceleration term, and the dA, the acceleration term in terms of A, acceleration, and the dA dt term. So you have 4 types of terms. Now, the approach that you've been presenting doesn't have that. And so you're missing a lot of the physics that's there. And it's all been confirmed in accelerator scattering experiments. But most people who haven't worked with accelerators may not be very familiar with that. But I did that for my PhD, so I had a little bit of experience with accelerators. And so those are the things that need to be taken into account. So it looks like in the approach that you're making, you're missing a lot of the key terms, which would be there if you use the complete set of the empirical laws of electrodynamics. And you were talking about not using special relativity. Well, special relativity is not a true theory, but if you use the complete set of the empirical laws of electrodynamics, you get some of the so-called special relativistic effects, but it has nothing to do with special relativity. It comes from Lenz's law. Lenz's law is not used in Oliver Heaviside's version of Maxwell's equations. And so you miss it. And also the quantum ideas also come from the dA dt term in electrodynamics, because there's some boundary conditions on that term, and the boundary condition tells you what the building block of all matter is, all electrodynamic structures. And it's like a toroidal ring, and that has a lot of properties that need to be taken into account. Well, that's just my comments.
Okay, great. Thank you.
All right, so let's get back to let's get back to what Bob has brought up about the what he was first talking about, which is the experiment that he brought up. So Bob, so I was listening to your presentation. So it seems that what your conclusion, it wasn't very clear to me, but you were just saying that by Weber's electrodynamics, it's like the current was the same. Is that what you were trying to say? I couldn't quite figure out what was the critical part of your solution there.
Yeah, for the Weber case, it doesn't matter what the velocity or acceleration of the inner ring or the outer ring is relative to the lab frame. What matters is their relative velocity and acceleration to each other. That was the point of the Weber approach.
I was doing some other work on trying to figure out how the magnetic field works. Now, basically, Weber, he basically ignores what's going on with the so-called magnetic field. Is that right? And only really deals with the what's going on with the electrons that are creating the magnetic field. Is that right?
My understanding is that in the traditional Weber electrodynamics, it's just the interaction between charged particles. And he doesn't talk about fields, electric or magnetic. It's an instantaneous action at a distance theory. And what I've done is I put in the fields. I say, and what I find is you really only need one field, the Coulomb field. You don't need to define a magnetic field. The magnetic field is a mathematical construct, not a physical construct. That was my development, my interpretation of Weber electrodynamics. So if you do want to talk about a magnetic field, that's fine, but that's not fundamental. What's fundamental is the moving charges that are, quote unquote, generating that field. But it's not generating a field, it's simply interacting with other charged bodies. And because there's a relative motion between the charged bodies, there's a force. That force equation has terms, and you can assign a name to each of those terms. One term may be the Coulomb force. The other term may be a magnetic induction term. These are just names. And then you can have a name for something depending on acceleration, and on and on and on, whatever the terms are in the force equation. But I look at it as one force, and so there's one field. And you can do the expansion of that force equation in different ways and come up with different terms. And that's why I say, well, you can give names to the individual terms if you want, but I'll expand it differently and come up with different terms. So what happens to your field if you assign a field to each individual term? So that doesn't make sense to me.
Yeah, I'm interested in that because I kind of came to that same conclusion that the magnetic field is kind of a made-up quantity. I mean, there is definitely something in space which is propagating it. But what's confusing, like in the unipolar induction case, you use the law where you have, so this is my Lorentz force law demonstrator here, where everything is at right angles. So it's like the pencil represents the motion of the electron, and then we have one that represents the actual resulting force, and that force is always going at a 90-degree angle to the direction of the electron, so it's always going to want to go that way. And then we have here, which is the direction of the prevailing magnetic force. All these things are at right angles, and it's very confusing to try and figure out, where the actual force is. But when I took an actual magnet and I put it on a television screen where I had drawn a simple cross, now instead of all of this B cross B stuff, I think it was much easier to just simply state that an electron will get deflected in the same direction as the coil of wire that would create that magnetic force. So if I took my magnet, I put a pole on there, it would just twist the cross to the right. And if you flipped it over, it would twist the cross to the left. Because if you're thinking about that magnetic field being created by like a solenoid coil, you can imagine that the electrons are sitting there and they're flowing in, say, this direction. And then when you put it up to the screen, you can see that it causes the electrons to also flow in the same direction as the electrons in the magnet. And if you put the magnet on its side, you can see it would basically drag down the whole cross, or if you flipped it around, it would drag up. But the point is that instead of the Lorentz force law, I came up with my new law, which says that the force of the magnetic field is proportional and in the same direction as the electrons, the moving current electrons that created that thing. So in this way, instead of looking at this, like everything at right angles, because this is really weird to understand how all these things can happen. But if you just think about it as just following the electrons in the magnet that's creating it, it's so much easier to understand. So I don't know if you understood any of that, but
Yeah, I don't know that it's so much easier to understand. If it's easier for you to understand, that's great. A lot of people just find the magnetic field conceptually very easy. And that's why I think it sticks around so much. It makes some problems very easy conceptually to solve, because you don't have to then trace out the individual electrons or charged particles that are moving. So I say if it works for you, great.
well, it kind of did for me. I mean, it's kind of came up in the context of, does the Lorentz force law apply always and everywhere? Because I was challenged in the email threads to explain why is it that in the presence of a magnetic field, a charge will trace out a circle, right? So I was trying to figure out, well, yeah, how does it do that? So in the presence of just a straight one line conductor, based on the way I see the magnetic field of just basically a polarization of space, that there's just no way that a charge would make a circle having a force on it at, say, 90 degrees to its direction of travel at all times, because that's what would happen if the force is at 90 degrees. It would just go in a circle, and the magnetic field in this case is always pointing in the same direction, which is what you would get from a single conductor. And that just didn't work. But when I went back and looked at what's really happening, which is that the electrons, and any electron approaching a wire, will just simply flow in the same direction as the current. So it's always going to just be deflected in this direction. It's never actually going to loop around. At least that would be my prediction. It's just going to flow with the current. And this is why I say it's much easier to conceive of it this way. And if that were true, then the Lorentz force law would effectively be wrong in that case. Now, I don't know whether that's true or not. I don't have any way to really experiment with sufficient sensitivity to see whether an electron really loops around or doesn't. But the thing but I still have to answer why is it we see electrons looping in magnetic fields. And what I've noticed that is that in all of these experiments where there's looping, there's like a large electromagnet or a very large magnet which is present, which is of course a large loop of wire. And if you think about the charge just trying to follow that loop, then in order to do that, it has to do a circle. So that's how I would explain how electron charges can circle without necessarily having the Lorentz force law being true. But that would be an interesting experiment because if it were true that along a single conductor that the electrons will only go in the same direction as the conductor. I mean, it can be thought of just like flowing water, and you put another thing there, it just goes with the flow. It doesn't go at right angles to the flow or anything weird like that. It just goes with the flow. Then that would be significant if we could disprove the Lorentz force law in that case. So does anybody else have any comments or about that, about the Lorentz force law or magnetism? You guys are a little bit quiet out there, so I'll continue talking to Bob about this unipolar induction thing. There have been quite a few discussions about this unipolar induction thing and why is it when you rotate the magnet with the disk, it still is able to generate electricity. Now, for my own opinion, I don't think it's that complicated. Applying complex Lorentz force law, that depends intimately upon the velocity of the electrons. And now Bob mentioned something about there being no B field, but quite clearly in the unipolar induction, the B field is totally present. So I'm not sure where he would get that because there's just a magnet right underneath the disk. So definitely the magnetic field is always there. But my solution to this problem has always been that since the Lorentz force law involves a velocity, that velocity always has to be measured relative to some frame. So on the Earth, what is the frame which determines experimental velocity here on Earth? So I am claiming that what the frame that determines experimental velocity on Earth is the ground. So here I'm sitting on Earth. The proper velocity for me sitting here in my room should be 0 miles per hour. And it shouldn't be like 300 kilometers per hour, which is like the velocity of the Earth, or 600 kilometers per hour, which is our velocity through the universe. That the proper velocity should always be measured relative to the ground for Earth-based experiments. So if we take that as our fundamental postulate, then we can see that in the unipolar induction case, that if we spin the rotator, that the electrons there will be taking on a velocity. And it doesn't matter that the magnet rotates with the disk, because the magnet doesn't determine the proper experimental frame for determining the velocity of the electrons in the unipolar inductor. So therefore, it doesn't make any difference whether the magnet is spinning or not. It has no impact upon either the direction or magnitude of the magnetic field. nor does it have any impact upon the velocity of the electrons in the spinning disk. So, in my estimation, one would expect that electricity would be generated in both cases following Lorentz force law and without introducing anything outside of the mainstream. So that would be my solution to that. That's too bad Harry isn't here. I think Harry would probably argue against that. Because a lot of people want to think that I think Harry's point is that the magnetic field lines are locked to the magnet. If you had, like, instead of a circular magnet, you had a rectangular magnet, and you can see that if there were magnetic force lines, that they follow the magnet around. But I think that's a red herring, because you're not measuring the field lines being locked onto the magnet. Here's Harry sending us a message right now. But you're just measuring the changing force lines. That the magnetic field is relatively non-moving. Does anybody have any comments on that? You guys are all just happy, just lurking. This is supposed to be a discussion, you know.
Relative,
like hearing me blab.
But relative to instruments that aren't spinning, though, they would be moving, though, wouldn't they? If you're measuring it from the ground that's not spinning, wouldn't the field lines be moving in that case?
Well, I don't feel that the field lines in a spinning magnet really move in any way. Is that what you're trying to get to?
Well, if you're measuring them from a stationary, something that's stationary to the magnet that's spinning, then they would be the magnetic field lines would be moving, wouldn't they?
I would argue not. I mean, but that's kind of in terms of my own magnetic theory, which is that it's a polarization of ether particles. So that if you take a magnet and you spin it, that would get these basically dipole particles to line up around the magnet so that they're just a big train of these things. But as you spin the magnet, it wouldn't change that alignment any. You would see that basically the dipoles are stationary and that there wouldn't be any actual movement. I mean, some people think that the way the magnet works is that it actually creates a vortex of moving ether around the magnet. I mean, that's kind of one way to explain what you see. If I take a magnet and I think of it as creating a vortex going around going to an axis through the poles, that what you see the electrons doing actually corresponds to that very well. So like when I took my magnet and stuck it up to the TV monitor, you can see it like created like a vortex pattern, as if there was like a little tornado going into the screen, pushing those electrons around in that direction. But personally, I don't think that the magnetic field is creating this vortex, an actual movement of some material in the space in front of it. Fundamentally, because if it did, then it would sweep up stationary electrons. A stationary electron in that kind of wind should feel a force. But we know that a stationary electron doesn't feel anything. It will feel zero force. So how can it be a wind around the magnet if it only feels it when it's moving? So the only way I can figure it would move, it only experiences forces when it's moving, is if it actually has to cut through these dipoles. Because when it goes through a dipole, the reason why it deflects is because one side of the dipole will be positive, one side of the dipole will be negative. So if you put a negative charge through, it'll be attracted to the positive side and will deflect upwards. And the only way it can deflect upwards is by actually cutting through a dipole pair. If it's just sitting there stationary, it will not feel any force. It'll just find an equilibrium position, maybe a little bit closer to the positive side, but it'll just stay there. It will not experience any force. So these are the mysteries of the magnetism that we have to figure out, which is, what in space is creating that magnetic force. So I wouldn't go so far as Weber goes and just say, just basically ignore that whole magnetic field thing. I think there is definitely something different about space which has a strong magnetic field versus space which has no magnetic field in it. So I think there's definitely a physical property there. So that's how I would explain why I think the magnetic field really isn't moving in the case of a symmetric rotating magnet. I think Harry would argue that that's not true because I can take a non-symmetrical magnet and I can see the magnetic field wildly varying. But I would once again say that that is actually a completely different case. That what's unique about the unipolar induction is that it is using a uniform circular magnet spinning on its axis, which in this case does not cause any difference in the magnetic field. It may be a special case because it's so uniform, but pointing out non-uniform cases doesn't really contradict the idea that in this case, we're looking at a completely uniform, non-changing magnetic field, whether the magnet is rotating or not.
Would your argument hold up if you were to shrink yourself to a very minuscule size and put yourself right up against the rotating magnet and hold out like a dipole antenna over the outer edge of the rotating magnet, and you would be so small that you can't even see that that magnet is rotating. To you, it looks like it's just going sideways. Would your argument hold up then?
Well, I think so. I think experimentally, there is nothing you can do to detect whether the magnet is rotating or not.
Right.
And if you didn't know the magnet was rotating, there's no experiment that you could perform that would tell you whether it was or not. I could be wrong about that, but I think that's what during the email exchanges, that's what came out of that, is that it matters so little that there's actually nothing you could do to tell whether the magnet, I mean, if you think about it intuitively, if I have like a super neodymium magnet and I'm detecting magnetic field with like a strip of iron or something, then whether I spin the magnet or not, the strip of iron is going to feel exactly the same force. My magnet detector cannot be used to determine whether the magnet is spinning or not.
Okay.
But that's an interesting question.
This question has been answered, some people think, by the work of William Hooper, because he measured the characteristics, the properties of 3 types of electric fields and 3 types of magnetic fields. And so he was able to distinguish between a non-rotating magnet and a rotating magnet by experiment. And so if you consider those experiments as valid, and as far as I know, no one has ever disproved them, there would be the ability to make those measurements. And one of the problems that we have with Maxwell's equations is that we don't take into account the different types of electric and magnetic fields. We just use E for the electric field and H for the magnetic field, or B, and we don't make a distinction, but experimentally you do. And so that's something that needs to be looked at. And I tried to look at some of that in my book on the universal force, but there's probably more that could be done.
Yeah, I'm not terribly familiar with being able to detect whether a uniform circular magnet is rotating. I mean, I thought that his main point was that that a magnet in motion has a particularly different force than a magnetic force which is stationary. That those, like the motional magnetic field can penetrate everything versus stationary magnetic field, which is easily blocked. So I'm not sure that had to do necessarily what we're talking about, which is, can you detect whether a uniform spinning magnet versus the same magnet not spinning. But it is an interesting question whether that can be experimentally detected.
Well, they can be detected by, for instance, putting it inside a metal box. And then certain types of electric fields and certain types of magnetic fields can get through the box. They cannot be blocked. But other types can. So with that, you can make a distinction between a rotating magnet and a stationary magnet.
All right. Well, while we got you here, Bill, so I just had got some recent bad news from my coworkers saying that she came down with pancreatic cancer, stage 4, which is terminal. Now, you have mentioned before that your wife has survived similar situations, right, using like a vegetable type diet. So
yes.
I don't know
and she's been well for 40 some years, and what seems to have happened is that we have made changes in the way we raise various fruits and vegetables and meats and things of this sort, and that causes us to have an imbalance in our bodies of certain chemical substances, and that enables us to get cancer quite easily. But if you go back to a true organic source of fruits and vegetables, such as the Amish would raise, then you can, just by eating that, you can get your body chemistry back into a more satisfactory mode, and your cancer will go away. And as far as they know, every type of cancer will respond to that. And but the government, the Food and Drug Administration, is opposed to that therapy. So if you go to a doctor and you have used that therapy, that doctor will be taken to court and his license to practice medicine revoked. And that happened in my wife's case. And so doctors are afraid to touch it. Even if they know about it, they won't recommend it. And when President Reagan had cancer, he didn't bother with any American doctor. He just went directly to Germany and got well in 2 weeks from his cancer. And he didn't want to cause a doctor to lose his license for practice medicine because he did something for the president. And so it's a sad situation. But there's also some other things that may be very practical, and that is If you saw the movie Star Wars, it's a science fiction movie. And in the science fiction movies, it used to be a practice to try and show future technologies that would be useful to people. And so one of the technologies they showed in the original Star Wars movies was a communicator. Now, at that time, there was no such thing as a cell phone in the United States. But after people saw that and realized it might be possible, they started working on it. And lo and behold, we have cell phones. And but there was another technology there called the tricorder. And when a person was sick, they radiated them with this tricorder. And this tricorder was based on the work of a French doctor who was drafted during World War II. And he was assigned to a radar unit, and he learned that there's a second type of radiation off of a radar antenna, not the normal type of radiation we call transverse radiation, but a longitudinal radiation. And he learned that that could heal animals and people. And he healed the wife of the president of France from terminal cancer, which no Western technology was able to help her. He healed her by radiating her with longitudinal radiation of particular frequencies.
Yeah, I think we've heard that story.
Yeah. So anyway, those types of things there. And by the way, the work that we were talking about earlier on the unipolar generator, the way we are looking at that electromagnetically, we're not taking into account the fact that there are two known forms of radiation, longitudinal and transverse. And the Maxwell's equations, the Oliver Heaviside version, only has transverse because he threw away all the terms related to longitudinal radiation. And throwing away terms when you're solving simultaneous equations is not the way to discover truth. You need to have a little bit of correctness, axioms, and the way you do proofs and that sort of thing in logic. That was all thrown away. And we need to get back to doing something that has a chance of being true, not something that just can explain some data and not other data. And so that's my comment on that.
Well, I wanted to get a little bit back about how your wife was cured. Now, she also had a terminal cancer. What kind was that?
She had melanoma level 4. That's where cancerous tumors are coming out all over the body, particularly in the glands that you have in your arms and legs and back and that sort of thing. So
yeah, stage 4. That's the last stage. So
that's right. And the next
stages after that.
The next thing they were going to do was remove her left arm and shoulder, to where the biggest original source of the cancer was, so that they thought they could give her another month or two of life by doing that. And my wife said, I don't want to have my left arm and shoulder taken off. I mean, it's just, you're not a person anymore. And so she refused to do that. And asked me to look for something different to do. And well,
you said
there were 200 patients, over 200 patients at the hospital where we were. We were at Georgetown University Hospital, which was.
I think that we've heard that story.
Okay.
And but what I'm interested in is exactly what you did. Now, you said that you went to these people who had this vegetable solution, but they're no longer in business, you said. So I think
the Food and Drug Administration went after them and shut them down. They have the power for shutting down anybody who does anything in the medical field.
I think you're our only source of information about this anymore, since I don't think anyone else will speak for it. So I was wondering if you could tell us, like, what is the regimen specifically, like what kind of vegetables and how were they prepared? Because you said that they they did this cleansing while you were there, and then they taught you how to keep it up, right? So,
Yeah, the purpose of staying there were two purposes. One was to put you on a fast to start cleaning out your system, and the second one was to start you on a diet. But most people were not familiar with all fruits and vegetable diet with no meat and no cooking and no processing of the food. And so they didn't know, well, what do I eat? What's the best thing? You know, that's what they would do there. So they spent a lot of time explaining to you the best fruits and vegetables to eat. And of course, you can't buy them at the grocery store. You've got to get them someplace like a Amish farmer's market. And and you need something that you can stand to eat, if you know what I mean. You can't just eat one particular thing. Like one of the best vegetables, if you could only eat one, would be eating celery. But most of us don't like to eat celery breakfast, lunch, and dinner every day. And but that would be like milk for a baby. You know, you can live on milk for a while because it's got everything you need at one phase of your life. But so that was the situation there. So what they did is every day you were there, and my wife was there for about 9 days. Every day she learned to prepare a new breakfast, a new lunch, and a new supper. No cooking, just fruits and vegetables. But
so what would be a specific breakfast? What would be a specific breakfast that you could prepare?
Actually, that was 40 some years ago. It would be I'm sorry, I'm
lunch,
having a senior moment here. I can't remember
it's been a while.
The things that we did. I ate the same diet with her so that we could survive, and so I should remember what it is, but it was a combination of fruits and vegetables, and I'm sorry, I just can't remember that. We no longer eat that diet. We eat a lot more fruits and vegetables than we used to, but we don't eat that diet that's 100%. So, but things like apples and apple juice, vinegar, those type things, all made from the apple, and carrots and celery, and many other, and also you can eat what do you call them, sprouts. They show you how to eat sprouts and things of that sort. So there was a lot there, but it's been a long time, so we haven't been doing that recently. So I'm sorry, I can't remember.
But basically, it kind of sounds like you need to go to the farmer's market, find the most organically grown vegetables. It doesn't sound particularly matters what kind, except you recommend celery, which I kind of find surprising because celery seems like the most nutrient deficient vegetable ever. But
no, that's not the case. It's actually one of the best. but if it's not organically grown, it can be a problem. And but if you go to an Amish community where there is, say, an Amish farmer's market, they will tell you who to go to talk to if you want to know how to do this sort of thing, because that the Amish community doesn't use doctors like we do. The Amish community handles a lot of those things within their own community, and so it's there would be someone there. Like I live in Maryland, and it's only about 1.5 miles from my house to the closest Amish farmers market, and so it's very common here, but many other people don't. Now, we didn't know about what the local Amish people knew. We went up to Pennsylvania to learn at a place where the Amish ran a special place called the Retreat House. And it was a place where you went and they taught you how to prepare breakfast, lunch, and dinner. And they also took samples of your blood and your urine. And from that, they did some chemical analysis to determine when your body was in the proper balance so that the cancer would go away. And when people first came there who had cancer, they wouldn't pass the tests for chemical balance. Their body would be out of balance chemically. And so that's what they emphasized. And
no one can do this test anymore, right? We don't even know what it was.
Oh, the test? Yeah, there was a name for that. There was a man down in Florida who devised the test for showing when your body was in proper chemical balance. And there was a woman who was kind of like a nurse who worked at this center, and she administered the tests and gave you your results. And I think there's some similar tests that some hospitals will do. I know when my wife went back to the hospital after she had done this treatment and therapy for 30 days, they administered some of these tests to her, and they said, your cancer has gone away. That's very days. Unusual. What did you do anything that caused it? And, so they knew from running these tests that the cancer had gone and the body chemistry had come back into normal range. That's
remarkable. You said just in 30 days?
30 days, yeah.
Just 30
President Reagan, when he had cancer, he got well in 2 weeks. he got a more elaborate treatment. But yeah, that's it takes a while for your body to recover when you're ill, just like any illness. It takes a while to stop the expansion of the fever or the whatever infection or whatever you've got, and then to recover from that. So that's why it took that period of time. And we weren't using any medications of any sort, just fresh fruits and vegetables. And in order to get the body to start being able to do that, we did fasting for 2 days. And and fasting apparently is, from all my health newsletters I get from time to time, a very good thing to do. And they recommend only fasting for 16 hours and then starting to eat again. Because if you fast longer than that, there's some negative effects.
Well, that certainly seems something that's certainly doable.
Yeah.
It's remarkable that anyone could go from stage 4 terminal cancer in 30 days, go back to the hospital and have them say that your cancer is gone.
Yes.
I don't even know that your body can clear cancer cells that fast.
Well, the cancer cells may still have been dead, but in the body. But your body does attack them and gets rid of them, turns them to something that can be taken away in the blood. And but there are chemical tests that can tell if you have cancer that are very sensitive. And a lot of people get that, and their doctor will say, oh, you got cancer, we got to find out where it is. It won't tell you where the cancer is, it just tells you if you have it. And those tests, I know many people who have cancer of the prostate first discover that when their doctor does a test and says, you got cancer somewhere in your body. And then he says, well, the most likely thing for a man would be in the prostate. So he goes and looks there first to see if there's something, and you can do an MRI or something like that and see if you have cancer in there. And
Well, I'll have to ask my doctor about that because I know they run a number of tests, but I don't know if they run a general cancer screening test.
It has a name.
Looks for those cancer markers.
They did that for my wife when she first went to a doctor, and she had a little cyst on her arm, and it didn't get well, and so she went to
The evening one was 6:30.
a doctor, and they ran this test and determined that it was cancerous, and they also found out there was more places in the body that had that same cancer than just that one spot. And so that's all I can tell you right at the moment. If you want, I could.
Again at the church, is it?
Who's that? Who was that was saying something? Is your house?
I don't know. That was a random conversation slipping through, I think.
Oh, okay. Sorry. But what I wanted to say is that this longitudinal radiation that the man in France used, it is now being developed in China. And they have taken the equivalent of a handheld laser, which is transverse, and converted it to longitudinal. And now they're trying to figure out how to get the different frequencies. And when they manage to achieve that, you may find an inexpensive device for just a couple $100 that can get you well from quite a few maladies by using longitudinal radiation. And so that is something that people should monitor if you're having trouble with that. And the man who used that, the French doctor, he was able to cure most diseases that animals get with that, not just cancer. I mean, many other diseases. And so it's quite remarkable. And I think the medical community is not interested in seeing that propagated, because you can take a man who's not trained at anything and give him one of these, and he can radiate a body of a person, and they'll get well, and they don't need to go and go to the drugstore and get anything. They don't need to go see a doctor. It's one of the biggest businesses in the world. And so they don't want to see the end of that business.
All right. Well, thanks for the additional information. I'll have to pass that on to my coworker. Yeah. That it is possible for someone in stage 4 cancer in 30 days to be cancer-free, which is a remarkable story.
Right. And if, I don't know, is this, where do you live? You're in Seattle. Seattle?
I don't know if there are any Amish around here.
Yeah, there may not be. They are in the eastern United States, Maryland and West Virginia and Ohio and Pennsylvania and those places, but I don't know. They're primarily farmers, so they're looking for good farmland.
Yep, maybe going to have them FedEx a box of Amish vegetables or something.
Well, I don't know about that, but you need to contact someone in the Amish community that can explain this a little better than I can right now. I had lots of material at one time. I gave it away to hundreds of people, and I don't have it anymore. They never returned it. They kept it. And some did recover from cancer using it. Some were talked out of it by their doctor, saying, "Oh, this no medical value here. We don't even recognize it in the medical community." And so anyway, I had a mixed experience with trying to help people with that, and I gave away all of my primary materials that I had accumulated. I do have health newsletters, and they talk about natural cures, and they involve eating some things for particular diseases, but they don't have the general approach. there.
Mhm.
And the
Yeah,
man who,
my office mate did mention something about doing nutritional approaches. So
yeah,
I'm sure she would be interested in hearing about that. It's too bad we don't have the details.
have her
But,
send me an email and I'll try and look up some of this stuff.
all right.
Okay.
Yeah, see what you can find. Because like I said, it's like been banned by the FDA. It's like you're the really only last hope because you
Oh,
don't.
I think there are thousands of people who have done it. I mean, I think is Reagan still alive?
No, I think he finally passed
He
away.
just finally passed
Old.
away. Well, anyway, he recovered from that problem, but he didn't recover from Alzheimer's, and so he had other problems. That
There are other problem. Old
and
age is a hard one to beat, right?
yeah, so yeah.
Okay, we're getting
Um,
kind of towards the end of today's presentation though, because I did have to cut things a little bit short. Did you have one last comment?
um, I wanted to say that we have a lot of data for electrodynamics and for particles. I mentioned Hooper's work on the fields, the property of the fields. He measured, I think it was 13 properties of electric and magnetic fields. And you could distinguish the three types of electric fields and the three types of magnetic fields by these properties. And so that was interesting. But also there's the work of Winston Bostick, who worked for Arthur Compton, the Nobel Prize winner, and Arthur Compton was the one that found the wavelength for the electron. No one was expecting a particle to have a wavelength, but he showed that experimentally that they did. And then
I still don't believe it, but
and then his last graduate student, which was Winston Bostick, did a whole series of experiments in which he was trying to basically answer the question, which is more fundamental, the particle or the field, the charge or the field? And so if you look in electrodynamics, like in Maxwell's equations, well, you've got both the charge and the field. But what Winston Bostick found in his experiments was he could manipulate the field and make what he called a charged particle, and it was a toroidal ring shape. And he mathematically would say, yeah, I can represent this field from this entity, this toroidal ring, as a charge Q, or E or whatever, and I can explain the field that you see around it in terms of that charge mathematically. But he said he discovered that it looked like the field was more fundamental than the charge, and you can have fields with no charge. And that when we look out in space, that's what we see. We see fields that go for many, many, many thousands of light years, it appears, and they wouldn't be there if they were coming from a charge. At such a huge distance, you wouldn't be able to measure it, but we're able to measure it, and it's really big. So anyway, those things need to be looked at, and Winston Bostick believed that the field was more fundamental than the charge. And when I got the general solution to the equations of electrodynamics, it turns out that you also get this impression that the field is more fundamental than the charge.
all right, let's see here. Well, that was my alarm going off telling me that I need to end the conference. So I think we'll end it here. So thanks for Bob, and thanks for giving us this information about more natural cures for cancer. And this week you also discussed a lot about, say, how magnetic fields work and how the unipolar generator works. And if anybody has any ideas to help out Bob with his proposed experiments to determine the difference between Maxwell's and Weber's dynamics to give him a shout and see whether you can do that experiment. All right, but that will do it for this week's episode of the Saturday Science Chat, and we hope to see you again next week.